This next section is looking at the particle-wave duality. And the photoelectric effect demonstrated that light, usually considered to be a wave, can also have the properties of particles, albeit without mass. That is, there's a wave-particle duality associated with light. Is there anything else that exhibits wave-particle duality? Particle properties of matter, electrons for example, are well known. And J.J. Thomson actually showed this in his experiment to determine a charge to mass ratio of an electron. And he generated a beam of electrons. When the electrons hit the screen, the beam gave rise to tiny flashes of colored light. So this phenomenon is best explained if we picture electrons as being particles. But does matter also exhibit wave properties? This question was thought about by a guy named Louis de Broglie. And this short little clip is going to give you a little bit of a background.
So in the early 20th century, physicists were bamboozled because light, which we thought was a wave, started to behave in certain experiments as if it were a particle. So for instance, there was an experiment done called the photoelectric effect, where if you shine light at a metal, it'll knock electrons out of the metal if that light has sufficient energy. But if you tried to explain this using wave mechanics, you get the wrong result. And it was only by resorting to a description of light as if it could only deliver energy in discrete packets that Einstein was able to describe how this photoelectric effect worked and predict the results that they actually measured in the lab. In other words, light was only giving energy in certain bunches equal to something called Planck's constant multiplied by the frequency of the light. It either gave all of this energy to the electron or it gave none of the energy to the electron. It was never half and half. It never gave half of this energy. It was sort of all or nothing. But this was confusing to people because we thought we had established that light was a wave, and we thought that because if you shine light through a double slit, if it were a particle, if light were just a bunch of particles, you would expect particles to just either go through the top hole and give you a bright spot right here, or go through the bottom hole, give you a bright spot right here. But what we actually measure when you do this experiment with light is that the light seemingly diffracts from both holes, overlaps, and it gives you a diffraction pattern on the screen. So instead of just two bright spots, it gives you this constructive and destructive pattern that would only emerge if the light beam were passing through both slits and then overlapping the way waves would out of two holes on this other side of the double slit. So this experiment showed that light behaved like a wave, but the photoelectric effect showed that light behaved more like a particle, and this kept happening. You kept discovering different experiments that showed particle-like behavior, or different experiments that showed wave-like behavior for light. Finally, physicists resigned to the fact that light can seemingly have particle-like properties and wave-like properties depending on the experiment being conducted. So that's where things sat when in 1924, a young French physicist, a brilliant young physicist named Louis de Broglie, now it looks like you pronounce this Louis de Broglie, and that's what I always said. I always read this and I said de Broglie in my mind, and I knew that wasn't right. If you look it up, it's more like Louis de Broglie. So get rid of all that, replace it with a Y in your mind. Louis de Broglie, in 1924, wrote a paper, and he did something no one else was doing. Everyone else was worried about light, and light behaving like a particle or a wave depending on the experiment. Louis de Broglie said this: what about the electron? You got this electron flying off here. He said, if light, which we thought was a wave, can act like a particle, maybe electrons, which we thought were particles, can act like a wave. In other words, maybe they have a wavelength associated with them. He was trying to synthesize these ideas into one overarching framework in which you could describe both quanta of light, i.e. particles of light, and particles, which we thought were just particles, but maybe they can behave like waves as well. So maybe, he was saying, everything in the universe can behave like a particle or a wave depending on the experiment that's being conducted. And he set out to figure out what would this wavelength be. He figured it out. It's called the de Broglie wavelength. Oh, I reverted, sorry. De Broglie wavelength, not the de Broglie wavelength. The de Broglie wavelength, he figured it out and he realized it was this. So he actually postulated it. He didn't really prove this. He motivated the idea, and then it was up to experimentalists to try this out. So he said that the wavelength associated with things that we thought were matter So sometimes these were called matter waves. But the wavelength of, say, an electron is going to be equal to Planck's constant divided by the momentum of that electron. And so why did he say this? Why did he pick Planck's constant, which, by the way, if you're not familiar with Planck's constant, it is, like the name suggests, just a constant. And it's always the same value. It's 6.626 times 10 to the negative 34th joule seconds. It's really small. This was a constant discovered in other experiments like this photoelectric effect.
And then we go on. So our book actually is a little bit more specific than just saying momentum, because we know that, let me go forward here, we know that momentum is mass times velocity. So we'll be looking at Planck's constant over mass times velocity. So looking at de Broglie, or Louis de Broglie, not de Broglie, that it looks like. I know, I also pronounce it like that too. It tells us that matter has wave properties. So we're able to measure the wavelength is equal to Planck's constant divided by momentum, or mass times velocity. Here we're given Planck's constant, so the matter has wave properties, not observable for big pieces of matter like golf balls, but for small pieces of matter like electrons. So for example, if it's something that needs to be measurable. So the product of m times v has to be very small, because h is so small. So like a golf ball, let's say this golf ball is 82.5 grams and it's moving at a velocity of 255 kilometers per hour, like 150 miles per hour. This m times v is going to be huge. So to have a wavelength of 1.13 times 10 to the negative 34th meters, that is such a small value, it cannot be measured with any instrument. So, and it's not a meaningful value. Because of this, wave properties are never assigned to any kind of massive objects. It is possible to observe wave-like properties only for particles of extremely small mass, like protons, neutrons, and electrons. For an example, here would be the wavelength of an electron. If I have here's my mass of the electron, and there's my velocity, my speed, and if I did Planck's constant divided by this product, I would get a wavelength of 2.43 times 10 to the negative 11th. Small particle, longer wavelength. Here's the sample problem. I want you to calculate the wavelength associated with an electron mass of 9.109 times 10 to the negative 28 grams that travels at 40% of the speed of light. Remember, the speed of light is 2.998 times 10 to the 8th meters per second. If I were to take my mass that I was given, the 9.109 times 10 to the negative 31, I got this number, 1.199 times 10 to the 8th, because I took 2.998 times 10 to the 8th and times it by 0.4 to get this. I have my mass, I have my velocity, and I have Planck's constant. So do Planck's constant divided by this product, and I should get 6.07 times 10 to the negative 12 meters. Convert our meters into nanometers, and we would have 1 meter on the bottom to 10 to the 9 nanometers on top to get 6.07 times 10 to the negative 3rd nanometers. Here's another one I'd like for you to try. Calculate the wavelength associated with a neutron that has a mass of 1.675 times 10 to the negative 24th grams, and it has a kinetic energy of 6.21 times 10 to the negative 21 joules. Knowing and remembering from way back when, Ke equals 1/2 mv squared. How does this help us get to what we need in order to find wavelength? So pause this, take a minute, try it out, and we'll go over the answer in a minute. All right, hopefully you had a chance to process this. First, I need to find the velocity because I was given the mass. So to rearrange 1/2 mv squared and solve for velocity, I would get 2,723 meters per second. Make sure that you get that. Again, this is 1/2 mv squared. I had to pull v out of it to get my velocity. Then I can plug it into de Broglie's equation. Planck's constant divided by m times v. And then again, once I get my answer, I'm going to times it by 10 to the 9th to get 0.145 nanometers. All of that leads us to our next section, the modern view of electronic structure, wave or quantum mechanics. So how does wave-particle duality affect our model of the arrangement of electrons and atoms? Well, 3 scientists helped contribute to this and provided our answer. We've got Schrodinger, we've got Born, and we have Heisenberg. So starting with de Broglie's hypothesis that an electron could be described as a matter wave, Schrodinger developed a model for electrons and atoms that has come to be called quantum mechanics or wave mechanics. So unlike Bohr's model, Schrodinger's model is a little more difficult to visualize, and the math equations are pretty complicated, but understanding it is essential to understanding the modern view of the atom. So first, he described the behavior of an electron in the atom as a standing wave. If you tie down a string at both ends, as you would like the string of a guitar, and then pluck it, the string vibrates as a standing wave. And you can show that there are only certain vibrations allowed for these standing waves, meaning the vibrations are quantized. Similarly, Schrodinger showed only certain matter waves are possible for an electron in an atom. Now, to describe these waves, physicists defined a series of mathematical equations called wave functions, which are designated, this wave function, by this Greek letter psi, psi. And when these equations are solved for energy, we find some important outcomes. These outcomes are: only certain wave functions are found to be acceptable, and each is associated with an allowed energy value. So the energy of the electron in the atom is quantized. And secondly, the solution to Schrodinger's equation for an electron in 3-dimensional space depends on 3 integers, n, l, and ml, which are called quantum numbers. And we're going to get into these quantum numbers in just a few minutes. Only certain combinations of their values are possible. An interesting little side note from the book In Search of Schrodinger's Cat. If it were ever possible to know the position and velocity of every particle in the universe, then it would be possible to predict with utter precision the future of every particle and therefore the future of the universe.
So like that just said, is it possible to know where every particle is in the universe? Here's a quick little video I want to show you about Heisenberg's uncertainty principle.
In the first year of my physics degree, I had a birthday party and 30 people came. In the last year of my physics degree, I had a birthday party and 5 people came. Now, it's not like physics turned me into a mega bitch or anything like that. At least, not that I know of. But as the years went on, I became more and more serious about my studies. I stopped going out with friends, meeting new people, and I spent most Saturday nights alone in my room integrating equations. The better my grades got, the more my social life suffered. This is just an example of one of life's many trade-offs. But trade-offs aren't just unique to us. They play a pretty big role in the way the world works. In this video, we're going to talk about the uncertainty principle. And you'll see that whether we're talking about position, momentum, good grades, or a social life, it all follows the same logic. There are some things you just can't improve without messing up something else. The most well-known version of this is probably the Heisenberg uncertainty principle from quantum mechanics. And while we will get to that today, the uncertainty principle is a lot more general. Let's start with something simpler. Say there's this little old lady, Mildred. Now you've been watching her for a week and you notice that on Sunday she goes to the market. Now, can you conclude that every Sunday she goes to the market? Well, not really. You've only seen her do it once. Now, you watch her for another week and lo and behold, on Sunday she goes to the market. So it's tempting to say that she goes to the market with frequency once per week. But it's still not enough. You need more time to draw an accurate conclusion. After a year of careful surveillance, you're pretty sure that she goes to the market with frequency once per week. But what if the next week she goes to bingo instead? Or what if she needs more cat food and goes twice? Really, you need an infinitely long time to be 100% sure that Mildred frequencies the market once per week. Obviously, you don't have an infinite amount of time. So the frequency of Mildred's market trips can never be known to 100% accuracy. There's this trade-off between knowing the frequency and spending time. This is a version of the uncertainty principle, and variables that have this trade-off relationship are called conjugate variables. Another more well-known pair of conjugate variables are position and momentum. This is one version of the Heisenberg uncertainty principle, and it states that the uncertainty in position and the uncertainty in momentum are always greater than or equal to this constant here. Basically, we can never measure both the position and momentum of an object to 100% accuracy. We'll come back to the equation in a bit, but first, let's talk about the intuition. The way my quantum physics professor introduced the uncertainty principle was, imagine you're trying to find the location of a basketball, But the only way you can do that is by throwing tennis balls at it and measuring where they bounce back. If you manage to hit the basketball, sure, you know where it was, but now it's moved. Keep the imagery in mind for this next bit. Heisenberg was a German physicist who loved classical music and was a pretty accomplished piano player. Oh yeah, and he won the Nobel Prize for the creation of quantum physics. One day he was performing a thought experiment. He wanted to see if he could measure both the position and velocity of an electron. To measure the velocity of something, you just need to measure its position twice and divide by the time it took between each measurement. So it seems silly that you could measure something once, but not twice, right? But the most direct way of measuring where something is to shine light on it, and from the reflected light, calculate its position. We do this every day when we look at things. Photons hit the object and reflect them back into our eyes. Then our brain figures out where it is from the image produced on the retina. So Heisenberg imagined looking at an electron under a microscope, firing a photon at it and figuring out the position of the electron. But in order not to move the electron, he would need to hit it with a photon of really low energy. Now, quantum particles have a property called wave-particle duality, where they behave as both particles and as waves. So while they can be thought of as particles, they also have a wavelength and frequency. Radio waves have the longest wavelength, 30 centimeters or more, and they're great for capturing images of stars and planets. But they'd be hopeless at producing a good image of, say, your face. You would just get a blur. See, you can't get better focusing power than the wavelengths that are forming on the image. The 30 centimeter radio waves can only make images of details at least 30 centimeters big. If you made the wavelength smaller, to about a millimeter, then you'd get a much better image. So if Heisenberg wanted to get a clear image of an electron, say to within a micron, he'd need to decrease the wavelength of the photon to within 1/1000th of a millimeter. But the energy of a photon is given by this equation, where E is the energy and lambda is the wavelength. So you can see that as the wavelength gets smaller, the energy gets bigger. If we decrease the wavelength, allowing us to get an accurate description of its position, the photon has to be of such high energy that it hits the electron too hard and moves it. If we hit the electron with a photon of low energy and then hit it again, we can get an idea of the velocity, but the images will be too fuzzy to measure its position with decent accuracy. This is a conundrum. Position and momentum are conjugate variables. You can't gain information about one without losing information about the other. Now let's come back to our equation. Hopefully now it makes more sense. These triangles mean uncertainty, and this x means position, and this p means momentum. This h bar on 2 is a teeny tiny little constant. Don't worry about the exact value right now. The important thing is that it's greater than 0. So the equation tells us that the uncertainty in position and the uncertainty in momentum is always greater than 0. Basically, we have to have some uncertainty somewhere. As we saw from Heisenberg's experiment, this had nothing to do with the equipment he was using. Unless we find a way to make wavelengths shorter without increasing energy, we're screwed. Now, for those of you who need a mathematical description to go with the intuition, don't worry, it's coming. When Einstein concluded that light behaved as particles, this French guy named Broglie made this outrageous, totally not founded on anything claim that all particles must behave like waves too. And he was right! The wavelength of an electron is just Planck's constant divided by its momentum. Therefore, the momentum of a wave can be represented by a wavelength. So say we know the exact momentum of an electron. We can represent it as a beautiful, infinitely long sine wave. But the position of the electron is also described by this wave. The area under the curve represents the probability of it being there, and we can see that we have basically no idea where it is. But waves have this cool property that when you add them together, they interfere and create a new wave. So say we're presented with this wave that describes the electron's position and momentum. Now the electron is much more localized and we have a way better idea of where it is. But this wave is made up of a sum of a lot of different wavelengths. And remember that wavelength and momentum are practically interchangeable. So then we no longer have just one momentum value. We have loads. So in gaining information about the position of the electron, we've lost information about its momentum.
Now, as we try to kind of wrap our brain around the modern quantum mechanical model, in Bohr's model of the atom, both the energy and the location, so the orbit that that electron was found at, The energy and the orbit that the electron and the hydrogen atom could be found were described accurately, so we knew those locations. However, Heisenberg postulated that for a tiny object such as an electron and an atom, it's impossible to determine accurately both its position and its energy. So any attempt to determine accurately either the location or the energy will leave the other one uncertain. So this is now known as Heisenberg uncertainty principle. If you choose to know the energy of an electron in an atom with only a small uncertainty, then we must accept a correspondingly large uncertainty in its position. So why is this important? Because we can assess the likelihood or the probability of finding an electron with a given energy in a given region of space. And because energy is key to understanding the chemistry of an atom, chemists accept the notion that knowing only the approximate location of the electron is okay. So the energy is what we're able to focus on.
The concept of quantum numbers is a bit intimidating because you're going to see a sequence of numbers that look like this. N equals a number, L, which is another number, ML, which is a third number, and MS, which is a fraction. And it's easy to go, what, oh my goodness, does this mean? So I want you to take a second and I want you to think about your favorite coffee mug or tea mug. And I want you to think about, what size is that teacup? Is it small? Is it medium? Is it large? Is it in between a small and a medium? So think of a scale of how big or small it is. Then I want you to think about, what shape is that coffee mug? And then, how is it oriented? Is it in your sink upside down? Is it on your counter right side up? Is it in your car maybe sideways because it's empty and you didn't have space in your cup holder for it? And then lastly, are you right-handed or are you left-handed? Is the handle typically on the right-hand side because you're right-handed and you pick it up with your right hand? Or is it on the left-hand side because you pick it up with your left hand? So there's lots of different positions and ways that your coffee mug could be oriented. For example, let's say that I have a coffee mug and on a scale of 1 to 6, I said that it was pretty small but not teeny. So I'm going to give it a value of 2. For the size. For the shape of my coffee mug, given 0, 1, 2, and 3, 0 meaning traditional, 1 is it's in the shape of a cylinder, 2 it's a big soup bowl, holds a lot of tea, and 3 it's a funky shape. I know my daughter has one that's shaped like an actual dog, and one that I would bring into class to show is shaped like Darth Vader. So is it a funky shape? Is it an animal? Is it the shape of something else? How is it oriented? Again, is it upright? Is it on its side or is it upside down? And the way that it's oriented is given a number value. And is the handle to the right or to the left? So in this case, the coffee mug that I'm describing to you is small, traditionally shaped, upright, and the handle is on the left. How would you describe how your coffee mug is located and the size of it and the shape of it right now? Why don't you pause and come up with 4 quantum numbers that would describe your coffee mug? So this is just kind of an idea of showing you how we can locate where an electron is located, what orbital it is, how far away from the nucleus it is, what shape the orbital is, and if that spin is up and down, and where in that orbital is it located. And we're going to get more into that in just a minute.
The wave function for an electron in an atom describes an atomic orbital. We know the energy of this electron, but we only know the region of space within which it is most probably located. When an electron has a particular wave function, and remember that wave function is psi, telling us that probability, it's said to occupy a particular orbital with a given amount of energy. So we're going to look at some of these different orbitals. Each orbital is described by 3 quantum numbers. Quantum numbers are terms that arise from the mathematics of the Schrödinger equation. They describe the location of an electron in a particular orbital, much like your house address. Each electron has its own set of 3 quantum numbers. The principal quantum number, n. This refers to, and the principal quantum number can have any integer value from 1 to infinity. The value of n is the primary factor in determining the energy of an orbital. It also defines the size of an orbital. So the greater the value of n, the greater the size of the orbital. 1, 2, 3, 4, all the way on up. But in atoms having more than one electron, 2 or more electrons may have the same n value. These electrons are said to be in the same energy electron shell. So if we're looking at our periodic table, Our periodic table currently has 7 rows or 7 shells of electrons. So N, thinking 1 through 7 currently. Then we have L, cursive L, our angular quantum number. So the orbitals of a given electron shell are then in subshells. So this is my electron shell, this is my subshell, where each subshell is characterized by a different value of quantum number L. This refers to as the orbital angular momentum. And it can have any integer value from 0 to a maximum of n minus 1. If my principal quantum number was 3, then this would be 3 minus 1, 2.
So that means that I could have an L value of 0, 1, comma, or 2. Those could be any of my L values. If my N was a value of 4, so if it was in my 4th energy level or row number 4, my L value would be 4 minus 1, so 3 would be my maximum L, but that also means it could be 0, 1, 2, or 3 for my L value.
This L defines the characteristic shape of an orbital. Okay, so different L values correspond to different orbital shape. For example, if n is equal to 1, then n minus 1 would be 0, and 0 corresponds to the S subshell. Remember when we were doing electron configuration and we had S, P, D, and F? S is our S subshell. We know that there's 1 orbital because we know that the S can hold 2 electrons. S is a spherical shaped orbital. If we had L of 1, that would mean that we had an N value of 2 because down here, 2 minus 1 would be 1. So if we had a 2, and if you think about this and you look at your periodic table, if I had an N value of 1, think about my first period in my periodic table. There's only S electrons, hydrogen and helium, right? I don't have 1 P electrons. So I can't have 1 here and then 1, a value of 1 here to have P electrons. Same with S, we have S, we have P, we know that we have D electrons. D electrons are in my 3rd energy shell, and if I have an N of 3, that means 3 minus 1 is 2, and if I look at this, L of 2 is equal to D subshell. So since N defines principal energy level, if there are N subshells, 1, we would have L as 0. If there was 2, if N was equal to 2, L can have values of 0 and 1. We know that in our 2nd energy level, in row 2, I have 2 S's and I have 2 P's. So I can have an L of 0 and 1. So I'm not just limited to saying N minus 1 is 1. I have 1 and I have 0 available. So S and P. 0 corresponds with S, right? And 1 corresponds with P. If I have 3, so my maximum L, 3 minus 1 is 2. I can have 2 and 1 and 0. So at N equals 3, I can have 3 D electrons, 3 P electrons, and 3 S electrons. And then finally, our last ML, the magnetic quantum number. This is related to the orientation in space of the orbitals within a subshell. Orbitals in a given subshell are different in their orientation in space, not in their energy. We can have a range from positive L to negative L with 0 included. For example, if L is equal to 2, all right, so let's say our L is 2. That means we have D up to D. We have S, P, and D. Then I can have plus or minus. So if we said if L is equal to 2, I can have minus 2 all the way up to plus 2. I could have negative 2, negative 1, 0, positive 1, and positive 2. The number of values of ML for a given subshell is equal to 2L plus 1. And that's the number of orbitals in the subshell. So if L was equal to 2, then that would mean N was equal to 3. So if I had something in my 3rd energy shell, so my L would be 3 minus 1, which is 2. That means I can have 2, 1, and 0 for my L's. I can have D, P, and F. And then to figure out quantum numbers, it's the integer between negative L and positive L. So if I said negative 2, negative 1, 0, 1, and 2. And how many would I have if L was 2? 2 times 2 is 4, plus 1 is 5. So I would have 5, 1, 2, 3, 4, 5 numbers. So then looking a little bit closer.
If our L was equal to 0, that means that our N is 1. In our very first row on the periodic table, there are only 2 electrons, and those 2 electrons are in our s orbital because the s can only hold 2. So we have n equals 1. Our L is equal to 0 because 1 minus 1 is 0. Now in our s orbital, s can hold 2 electrons like we said, and we denote this by ml as being 0. This can hold 1, 2 electrons. So in the s orbital, there is 1 orbital for those 2 electrons to be in. Now if L was equal to 1, that means that this is s, this is p. So in row 2, so we would need n to equal 2. 2 minus 1 is 1, so we could have s and p sublevels. Therefore, I can have, in a p orbital, I can have -1, 0, or +1 suborbitals. Because we know P can hold 6. 1, 2, 3, 4, 5, 6. So this is getting just more specific on which orbital in that P subshell would those electrons be found in. So again, we would have -1, 0, or +1, which is why it says our ML values can be 0, +1, or -1. Same with if I said it was in row 2, maybe it's not positive or -1 because if it was in S, if it's a 2S, then its value is only going to be 0. If it was 2P, then we add those extra areas for those electrons to be found in. If it was in D sublevel, see where it gives all of these other places, because D, if you count on the periodic table where the D block is and count from left to right, there should be 10 atoms, which means 10 electrons. So if we said 0 plus or minus 1 plus or minus 2, 2, 4, 6, 8, 10. I always, when I look at this, I put 0 in the center, and then I go -1, -2, +1, +2. So again, electrons can be found 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in any of those places. So if it was in the D block, it'd be in any of those ML positions. If it was in the P block, it'd be any of these. In S, the only option is 0.
We know orbitals are where an electron can be found in an atom. We know that they have a characteristic size and shape. N, L, ML, all right? We just covered all of this.
And that brings us to our last quantum number, which is denoted as MS. And that is looking at the spin. Now, each orbital can only accommodate 2 electrons, no more. And we're going to talk about some rules about how those electrons can be in an orbital and how they fill up those orbitals. But for right now, all we need to know is the last piece of that address. You can live in the same zip code as a lot of different people. You can live in the same city as fewer people, so we're starting to get more and more specific. Then we can get to your street name, and there's a lot of people that live on your street, but then we get to your specific address. There are no 2 houses at your specific address. Even though you have neighbors, their numbers are a little bit different. So this MS is what really narrows down the location of that electron, and it's by spin. We denote MS as either +1/2 for the spin being up or -1/2 for the spin being down. And we will get more into looking at these 4 quantum numbers in just a minute.
Here's a little bit of a summary. This all helps us describe an orbital. A set of 4 quantum numbers describes an electron. No 2 electrons can have an identical set of 4.
Well, we've talked about s orbitals, and you know that it can hold 2 electrons. It's the first 2 groups or families on the periodic table. But s orbitals have a spherical shape extending out from the nucleus. P orbitals are shaped kind of like a circus peanut, like a dumbbell. And we can see the shape of this p orbital. We know that it can hold 6 electrons. The p block on our periodic table extends from group 3a or 13 through 18 or 8. Then we have our D block, which is our transition metals. We know that they can hold 10 electrons, and these d orbitals are shaped like a double dumbbell, so 2 p orbitals kind of crisscross with one another. And f orbitals, they can hold 14 electrons. Those are the lanthanide and actinide series at the bottom of the periodic table that are in periods 6 and 7. And basically, you just need to know that those are complexly shaped.
Which of the following numbers is not a valid set of quantum numbers? So if I had n equals 4, can L equal 1? And can there be ML of -1? N is equal to 6. That is equal to 2 if N is equal to 3. Hopefully you would look at this and you would go, well, L has to be at least minus n minus 1. So yes, 1 is a possibility for L. That's less than 1. This is less than 1. But we can't have L equal to, so this would not be possible. How about this? For a certain orbital, if n is equal to 3, L is 1, and ML is negative 1, what type of orbital is this? If you were to just go off of what you know. Hopefully you're understanding that this is which period we're in. So we're in period 3, and remember L corresponds to the shape. So remember 0 is S, and then P, and then D, and then F. So 0 is S, 1 is P. So this is a 3P orbital. What about this one? If an electron subshell has 7 orbitals, what is the L value for this subshell? Well, we get orbitals by 2L plus 1. So we would need to do 3 times 2 is 6 plus 1 is 7 would give me the 7 orbitals. So answer has to be 3. A complete description of an electron in any atom requires 4 quantum numbers, N, L, ML, and MS. This final property wraps up our chapter 6, which is the structure of atoms. So please refer to the module for some supplemental materials and extra practice homework problems.